Hello and welcome to the Daily Space. I'm your host, Dr. Pamela Gay,
And I am your host, Beth Johnson.
and we are here to put science in your brain. As much as we enjoy studying the skies strictly for scientific reasons, sometimes it turns out there are less inspirational reasons, like making sure our planet doesn't get destroyed by incoming asteroids. Our solar system is filled with rocks, and while we'd like to think we found all the largest ones, the truth is, there are probably some space rocks capable of ending humanity still not discovered. And there are definitely objects big enough to destroy cities still missing from our catalogs. To fill in these gaps in our maps, a number of telescopes are regularly monitoring the sky. Here in the Northern Hemisphere, we are pretty full up on surveys. But in the Southern Hemisphere, there have been gaps in the coverage. Gaps a new telescope in Chile hopes to fill in. The European Southern Observatory and the European Space Agency have jointly completed construction of a new 56 centimeter telescope that is a twin to an existing telescope in Spain. Together, these scopes are testing new technologies that may be deployed in the future in a fly eye telescope network designed to track fast moving objects in the sky. These kinds of systems are particularly good at providing early warnings for incoming smaller bodies, like the meteor that struck in Botswana that we discussed last week, and the 2013 Chelyabinsk meteor event. Since the Earth's surface is mostly water, we don't actually know how common these kinds of events are. And I both dread and am excited by the prospect of these scopes discovering a lot of space rocks hitting Earth in harmless places.
Asteroids and fallen smaller meteorites are responsible for a lot of different things in our solar system. For instance, moon dust. Space rocks striking the surface of the moon have pulverized its surface into sharp dust that ranges in size down to nanoparticles, capable of irritating skin and damaging lungs. When not irritating astronauts, these tiny fragments are also responsible for giving the moon its colors and defining how much light it reflects. In a new journal article in IEEE Explore with first author Soman Badia, researchers discussed how they used tiny X-ray wavelengths of light to examine the shape of particles just 400 nanometers across. Several hundred of these particles could fit across the diameter of just one human hair. Just measuring these grains is remarkable. According to researcher Edgar Bogi, since they are so tiny and because they only come in powders, a single particle needs to be separated from all the others. They are too small to do that by hand, at least not in any quantity, so they must be carefully dispersed in a medium. The medium must also freeze their mechanical motion in order to be able to get a good X-ray CT image. If there is any movement of the particles during the several hours of the XCT scan, then the images will be badly blurred and generally not usable. The final form of the sample must also be compatible with getting the X-ray source and camera close to the sample while it rotates. So a narrow, straight cylinder is best. So basically, they made fancy moon dust popsicles, looked at them with X-rays, and got remarkable images of the dust grain shapes. Those shapes, depending on how round or elongated they are, give the moon its colors. This final what does each shape mean work is ongoing. Today, I just want to celebrate that they measured the shapes. And if you're imaging fancy high-tech setups, now we are celebrating the spirit of the tinkerer. According to the release, the procedure involves stirring the Apollo 11 material into epoxy, which was then dripped over the outside of a tiny straw to get a thin layer. Small pieces of this layer were then removed from the straw and mounted on dressmaker's pins, which were inserted into the XCT instrument.
As NASA plans to go back to the moon and eventually journey to Mars, a lot of energy is going into dust mitigation so that tiny, sharp dust stays away from humans. And they're also working to figure out how to build suits that allow astronauts to explore safely and easily. One of our big concerns with Mars is also radiation. And one of the ways to best escape radiation is to live and work inside a lava tube. To this end, researchers have donned spacesuits to explore Hawaiian lava tubes to figure out what is and isn't possible and what problems need to be solved. This research is being presented at the European Geological Assembly's meeting this week by Bernard Foyng. According to co-researcher Michela Maselava, doing research in suits under EVA constraints makes everything much more difficult to do, and it all takes 3 times longer. We need to train extensively on Earth to figure out the best methods and create the best EVA suits so that we'll be able to perform this kind of research on the Moon and Mars one day. This is your reminder that for every great accomplishment off the Earth, there has been countless hours of development, testing, and training here on Earth, both in giant pools and in high desert environments, testing and training that's done by folks whose names are rarely mentioned and whose faces, well, those are hidden in these amazing helmets. After the break, we'll be back to discuss something I didn't think could exist: antimatter stars. Hang on, things are about to get a little weird. So, when you study astronomy, and people learn that you study astronomy, you get asked lots of questions along the lines of, could there be antimatter stars? Could there be antimatter galaxies? Could there be dark matter galaxies? And while we think we have found galaxies made out of dark matter, I think most of my colleagues have gone through life saying, no, there are not antimatter stars. And we might be wrong. And this is why we do science. We want to figure out what is real about the universe, and we recognize we don't actually know everything. We are just trying really hard to know everything. Now, there are 2 kinds of matter, and we're really bad at naming things. There's the stuff we're made out of: electrons, neutrons, protons, regular matter. But all of these particles have an antimatter version. Neutrinos have an antimatter version. And if you've watched Star Trek, you know that controlled reactions with antimatter generate a ton of energy. Now, this is because if you put a regular electron and its antimatter cohort, a positron or anti-electron, together, they're going to combine into energy. It's awesome, and luckily doesn't happen all the time. For the most part, when particles come together, the reactions aren't right to release energy. Antimatter neutrinos are passing through you constantly. No big deal. But for reasons we don't know, our universe probably formed with equal amounts of matter and the opposite charge, otherwise identical, has gravity working in the same way, has mass working in the same way. It's just that charge that's different. The universe probably formed with equal amounts of matter and antimatter, and then something went sideways, and we got left with a universe that is pretty much all matter. And we thought that meant no antimatter stars. But a group of astronomers has gone through the Fermi Gamma Ray Telescope's data and discovered 14 different flickering spots in the sky that give off flashes of gamma ray light that are consistent with those 14 sources being antimatter stars. How this happens, no idea. Is this what actually happened? No idea. This is one of those times where you look at something, there are a variety of options, and one of them defies all expectations. So those 14 flickers are consistent with antimatter stars. That means somehow our universe had clumps of antimatter that survived in the midst of all the matter or managed to form later. Those clumps of antimatter collapsed down into stars. And because matter and antimatter look identical in how they do fission and fusion and all those sorts of things, those stars would be shining just like any other star, except when a bit of actual matter hits them just right, gamma rays happen. Gamma rays, people. Now, normally I would simply look at this research and go, that's cool, don't believe it, and set it aside. The reason I didn't entirely do that today is because an experiment aboard the International Space Station captured evidence of random antimatter helium, just kind of hanging out, existing as helium atoms do, except it was antimatter helium, folks. Antimatter helium. And the best way to explain that is if there's antimatter stars. Again, this could have an entirely different explanation. We do science to figure these things out, but the universe just keeps showing us it's more creative than we are in coming up with theories. And so we have two lines of evidence: random antimatter helium detected by the International Space Station experiment, and 4 sources of flickering light. Now, if there are antimatter stars out there, they probably aren't common, or we'd see a whole lot more flickering. Based on the density of the kind of material that's hanging around and would be hitting these antimatter stars, if they exist in the disk of our Milky Way, which we'll talk about more in a later segment, if they exist in the disk of our Milky Way, they'd only be 1 in every 400,000 stars, because there's so much stuff floating around that would be hitting them that they'd be twinkling like Christmas lights, but in gamma rays. If, however, they're super rare and they only exist in the outskirts, the halo of the galaxy, there could be as many as 1 in 10 stars out there that are antimatter, and we just don't see them because there's not a lot of stuff hitting them, causing them to flicker. Again, I'm not saying we found them. I'm saying there's some cool stuff going on we don't understand. And one really weird explanation that I would never have expected to see is that there's antimatter stars. This work is published in Physics Review D by Simone Dupoquet, Luigi Tebaldo, and Peter von Balnos. We're going to follow this story, folks. I don't know where it's going to go, but that's going to happen on another day. For now, we're going to go to break, and when we come back, we're going to be talking about chemistry out there on other worlds. Stay tuned.
It seems astronomers are always searching for something new, something special, something groundbreaking that will lead us on to the next big discovery. And while antistars are incredibly fascinating, and I hope we discover them, I'll be over here watching as our ability to detect certain particles in the atmospheres of exoplanets continues to grow. In a recent paper in the astrophysical journal Letters, an international team of astronomers reports on finding hydroxyl, that tiny molecule consisting of 1 hydrogen atom and 1 oxygen atom, in the atmosphere of superhot Jupiter WASP 33b. Now, when I say super hot, I mean that because this planet orbits its star at a distance closer than that of Mercury to our own sun, atmospheric temps reach more than 2,500 degrees Celsius. That's hot enough to melt most metals, y'all. Finding hydroxyl on a hot Jupiter isn't just exciting for the discovery itself, but also for the upgrade in technology that allowed the team to make the discovery. A new instrument at the Subaru telescope in Hawaii called the infrared Doppler uses absorption spectroscopy, dark lines breaking up a full rainbow of light, to detect the fingerprint of various molecules. The instrument works by using the Doppler shift of the light as the planet's velocity changes relative to Earth while it orbits its host star. Basically, we can use those changes in velocity to separate the planet's characteristics from the stars, since the star's velocity doesn't change, again, relative to Earth. And then we match the dark lines with the known patterns of a variety of atoms and molecules to figure out what is in the atmosphere. Hydroxyl is an important molecule to find. Here on Earth, it's produced by the reaction of water vapor with atomic oxygen and is considered an atmospheric detergent because it reacts with polluting gas like methane and carbon dioxide to essentially remove them. In the case of WASP 33b, though, the hydroxyl is produced by the destruction of the water vapor under the high heat of the star. And confirming the likelihood of this explanation is the very weak signal of water vapor in the data. But why bother with hot Jupiters? As co-author Dr. Neil Gibson states, the science of extrasolar planets is relatively new, and a key goal of modern astronomy is to explore these planets' atmospheres in detail and eventually to search for Earth-like exoplanets, planets like our own. Every new atmospheric species discovered further improves our understanding of exoplanets and the techniques required to study their atmospheres and takes us closer to this goal. And co-author Chris Watson adds, while WASP 33b may be a giant planet, these observations are the test bed for the next generation facilities like the 30-meter telescope and the European Extremely Large Telescope in searching for biosignatures on smaller and potentially rocky worlds, which might provide hints to one of the oldest questions of mankind. Are we alone? We'll be back in a moment to round out our show with this week's What's Up segment.
Tis the season for galaxy observing, or at least for observing our galaxy from edge to core as the world rotates. If you live in a particularly dark area, you can go outside right now after, well, twilight has totally ended and watch the brightening glow of our disk of stars and dust and gas begin to light up in the sky. Now, early in the evening, what you're going to see is looking out away from the center of the Milky Way. So you're looking out through the disk, bulge behind you, out to the universe beyond. Now, the thing is that as you look at that Milky Way, it doesn't really appear any different when you're looking straight out and when you're looking at a right angle through the disk. In fact, throughout the night, as the sky rotates, it's not until you get towards dawn and the rise of the constellation Sagittarius that you're gonna start seeing things change dramatically with the rising of the bulge. This lack of difference made it really hard for early astronomers to figure out where we are in the Milky Way because the dust and the gas just obscure stuff. And we know which direction the center of the galaxy is in only because it gets thicker there, and we can see that. In order to figure out where we are, astronomers actually had to look out of the disk at those faint fuzzy objects called globular clusters. We know they form roughly a spherical population around our galaxy. And so by measuring the distribution of them, assuming that they're in a sphere, we were able to figure out we're a fair ways away from the center and the disk. So right now, good time to get out and look up. Now, if you're in the southern hemisphere, you get to see some amazing things we don't get to see up here in the north. Specifically, you get to see the large and small Magellanic Clouds, which kind of look like someone took a handful of the disk of the Milky Way and just cast it off sideways, splatting two splatters of stars. Now, throughout my career, I've seen people discuss, are these or aren't these going to merge into our galaxy and become a new part of the Milky Way? And the answer, it turns out, is it's up to dark matter. We just don't know. But we're getting closer to finding out. There's a new paper in the journal Nature, and researchers are discussing imaging campaigns led by Charlie Conroy that studied the effects of the Large Magellanic Cloud on our galaxy's halo as it passed through. It has long been thought that this small galaxy and its visible matter and dark matter should leave a wake in our galaxy's visible and dark matter. So you have galaxy of stuff passing through our galaxy's outer distribution of stuff. to back out and take a look at exactly what is going on. We have our galaxy, the spheroid around it, and then the large and small Magellanic Clouds racing through that spheroid of material. Well, we assumed that just like a boat racing through liquid, these galaxies would leave a wake. We hadn't seen it before. This is the first time we've been able to make out how the Large Magellanic Cloud disturbs the Milky Way's dark matter. And it's going to allow us to start understanding some new properties of the dark matter. Think of it this way. The wake of a boat varies depending on if the boat sails in water or glycerin, the stuff they use to make your shampoo the consistency it is. Folks, if you don't know what this looks like, this is an experiment we did with undergrads when I used to teach. You can take toy boats and sail them in water and glycerin, and it does not work the same way in both cases. Now, with our researchers, here's how they're explaining it. It's a really special set of circumstances that came together to create this scenario that lets us test our dark matter theories. This is a quote from Gurentina Besla, a co-author of this study. I can't wait to see what they learn from this wake they have discovered. Science can be beautiful, amazing, and slow. These stories will be discussed more in future episodes as this research advances. For now, this has been the Daily Space.
You can find more information on all of our stories, including images, at dailyspace.org. As always, we're here thanks to the generous donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.